you very much, first of all, for everyone to attend today. I think we are a quite large group right now, which is pretty cool. First of all, I would like to greet everyone. Nice that you're here, and we are indeed very, very happy to have organized such a great event again, so now for the 5th time. And herefore, I first of all like to thank everyone that have helped and have contributed to this event. And also in these COVID-19 times, it may feel also like to bring back a little bit of the normalcy back to the university and back to also our community. So we're actually here today to share our research ideas, to network with peers across Europe and Eurasia, and to develop a little bit of science communication for everyone. And therefore, we have our event today. So today we are having, maybe I share my screen for that. So do you see our program now?
It's flashing at us.
All right, so I stopped sharing my screen. I'm sorry.
There you go.
Here we go. Thanks. So exactly. So first of all, we're having 3 different sessions with all in all 10 students, 9 students that would like to present today. And for each session, we have 2 different chairs that will guide us and ourselves through the session and through the whole conference today. For all presentations, we have all in all 10 minutes of presentation, and afterwards up to 5 minutes for questions. And these questions, there are actually 2 options to how they can be asked later. So first of all, we have a Q&A section in the comments, and the chairs will read out the questions loud afterwards, so you can just type them in there. Or the second option is there's a button that says raise your hand, so you can push that button and the chairs will unmute you for questions later on. And last but not least, I would also like to inform everyone that this event is recorded and afterwards hopefully uploaded to YouTube. So you can also see how you performed or also share the link with everyone and share the talk with everyone who is interested. So from my side, I would like to wish everyone good luck and much fun today. And with this, I would like to give my words to Ivan.
Yes, good afternoon, everyone. I'm very glad to see you all here. My name is Ivan. Here I present SEG from Moscow, and I co-chair with Robert. Let me explain or remind you the price system of this conference. There is $1,000 at stake today. Third place we received $100, second place we received $300, and the first prize is $1,600. I would like to say a huge thanks to the SEG Foundation for these funds, in general for the very fact of the student virtual conference at all. It is an amazing opportunity for future scientists and professionals to show themselves at all European level. So on behalf of all student community of SEG, I guess I want to express our gratitude to you. Without you, this conference would not exist. Now to the system of evaluation of papers. The first point, technical veracity, works with well-supported scientific content will receive the highest score. Then significance of your work, of your scientific work. Its breakthrough effect. Then will be evaluated structure and the illustrations and the grammar of the speech. Then evaluation of the conclusion. Well-structured conclusions are important. Then commercialism and then delivery. Outstanding and captive talk will receive the highest score. All of these points are scored from 1 to 5. The best work, in the personal opinion of jury, can also receive up to 3 points extra. We would like to specify that one of the organizers also take part in the conference as the participant. It's Tatiana. Her work will be out of the prize program and will not be evaluated. And now I ask you, dear presenters, to turn on your cameras. If you don't, let's create a presence effect to unite all Eurasia and Europe here now. Well. When the cameras are on, all that remains is to wish you good luck and more important, to enjoy yourself here. Well. And now let me give the floor to the president of SEG, the Honorable Miss Anna Shaughnessy.
Thank you very much, Ivan. I'm very delighted to be with you here today. I come to you from Massachusetts in the US, but I wanted to let all of you know that I originally come from Europe. I'm originally Swedish, and it's where I got my undergraduate, and so it's a real pleasure to be with you here today, and hopefully encourage you and let you know that Europe plays a big role within the SEG, and we really appreciate your involvement, and we want you to get even more involved. I personally think it's fantastic with student conferences, and I'm delighted to see the variety of different talks that you're giving today. It spans a lot of different topics, which is something that I'm going to talk a little bit about. So I'm going to share my screen, and let's see here. If someone can tell me if they can see my screen here in a second.
I can see it.
And
okay. Yes, it's
okay.
Perfect.
So this is me, Anna Shaughnessy, and we're here at this virtual student conference. And first, I just wanted to tell you a little bit about what SEG is involved in today. First of all, of course, energy. We've been part of the energy industry for a long time. We are experts at exploring for and developing oil and gas, but that's not the only thing we're involved in. It's many, many different things. We are, of course, part of the digitalization effort. We are drivers of machine learning and artificial intelligence. You know how the different data sets we have that we need to combine, they are becoming more complex, more large, diverse, etc. We have always been engaged with our sister science societies. We have a lot of different meetings with them. I'm sure you've attended some, whether it's with EAGE, SPE, or others. And we are trying to work even closer with them now on some of the topics related to the energy transition, such as carbon solutions, geothermal, and any other type of renewable energies. We have initiated a medical imaging task force. In essence, we firmly believe that our experience in imaging could help the medical field. We've been involved in environmental geophysics for a long time. Of course, through our program, Geoscientists Without Borders. I hope you're all familiar with it, and if not, please go and look it up. But we're seeing a real growth in environmental, in near surface geophysics. We are seeing all sorts of efforts when it comes to water management, infrastructure monitoring, etc. And things like slope stability. I know we have a talk today about quicksand. So there are quick clays. There are all sorts of different work in this arena that I personally think is going to grow as we look towards creating a sustainable world. We've always been involved with academia. I think that it's extremely important at this time that we engage and invite in the best students ever and get them excited about what geophysics and geophysicists can do. I think we also have to influence academia and encourage them to offer topics that are becoming more interesting and important going forward, related to things, again, like carbon solutions, maybe mining, geothermal, etc. And of course, there's a lot of research going on in academia that we support as well. And we have a planetary task force. We haven't really gotten that far yet, but we'd like to see if some of the methods that we use on Earth could be used for planetary geophysics. So these are all the things that we are involved in today. There could be more going forward, or there could be fewer. And actually you have an input into that decision. I wanted to make sure that all of you have seen the article, the Geophysical Sustainability Atlas. It's mapping geophysics to the UN Sustainability Development Goals. It was the brainchild of Maria Angela Capello, and it basically is an article that shows how geophysics influences all the different SDGs, from no poverty to zero hunger to climate action, etc. I would like to think that these are topics that are important to you. This article was published in the Leading Edge in January of this year. And to me, it provides a tool to talk to people, not just within geosciences, but to other groups, whether they are environmental groups, whether they are policymakers, whether they are family members. And I encourage you to read it. And I would like to point out that this article was published as open source thanks to the SEG. And so I hope you will read it and share it. And you can see the link there. And I'm hoping that Laurie or someone can put that link in the chat so that you download it and take a look. It's just a first step. It's not a final product. We're looking at continuing this effort to make sure that everyone appreciates what the geosciences can do for sustainability. I wanted to just briefly talk about some of the things that SEG does for students. You can see the link to all the information on our website, but we have scholarships. In fact, you can see there it's open enrollment right now. These are global scholarships. We have a student leadership symposium. Again, applications are due starting the new year. We have a near surface awards, and we have several different types of grants, from travel grants. We sponsor field camps. And of course, we sponsor student chapters. And to me, there are benefits in all these different things. Some of them, of course, are monetary. But to me, the benefit of belonging to a student chapter, maybe taking a leadership role, whether you're the president, the treasurer, or the person that organizes an outreach to a high school, etc., these are things that you can put on your resume. And these are things that can make a difference if there's a competition for a job. If you can show that you've been proactive and taking leadership roles in different arenas, it's a great thing to boost your resume as well as boost your confidence. So take advantage of some of these things. We also have a mentoring program, Mentoring 365. There's an Evolve program, which is an experiential learning program. So take a look and make sure you see what appeals to you and where you can make a difference and participate. So I just wanted to briefly say SEG in the future. We are basically up for a big decision this year, whether we want to be an industry society or a technical society. And why is that? Well, it's because the landscape for science societies is changing. And two of our largest sister societies, the AAPG, American Association of Petroleum Geologists, and the SPE, Society of Petroleum Engineers, have decided that they want to merge. We have been invited to merge, and we're looking into that. We have a very small team looking into that, but we're also looking at other options going forward. And we've created a strategic options task force to see what other directions could we go? Are there other societies that we could collaborate with? Can we be an applied geophysics society that includes all the different types of geophysics, as opposed to just focusing, or more or less focusing, on energy or petroleum? So these are things that I would love for you to take a look at and think about within your chapters, between your peers. And if you're a member of SEG, you should have received a letter yesterday via email that talks about this task force, and it gives you an email link to where you can give input, basically directly to the task force. So think about that, because in my mind, you are the influencers going forward, and I would like for you to really take part in what SEG should look like, not just 5 years from now, but 10, 15, 20 years from now. So that is what I would like to say, and I thank you very much for your attention, and I wish you a great virtual conference. Thank you so much.
Thank you so much, Anna. That was really interesting. Great to see where the SEG has been and where it's heading. And as someone that actually participated in the Student Leadership Symposium, I can definitely encourage everyone to have a look at all the programs that the SEG offers. But let me not hold up the presentations any further. I'm sure people are desperate to finally hear some research. So I would like to introduce our first speaker of today in the session, Seismic Applications. This will be Alexandra Lomakina. I'm sorry for butchering your name. And she will talk about the selection of pre-stack time migration or pre-stack depth migration, depending on the degree of environmental heterogeneity. So Alexandra, the floor is all yours. Good luck and enjoy.
Thank you. I will share my screen. Can you see it?
Yes.
Thank you.
Needs to be placed in slideshow mode.
Can I start?
Please, yeah, go ahead.
Thank you. Hello, everyone. It's good to see you all today. My today's topic is the selection of pre-stack time migration or pre-stack depth migration, depending on the degree of environmental heterogeneity. My presentation will take about 10 minutes. So let's start with the brief theoretical basics of migration. Post-stack or zero offset migration, what is it? As you can see, the deeping event has moved to a new position and appears to have a new deep. So an objective of migration is to reposition the deeping to appear more like the geological structure. In the other words, the migration puts the recorded data back where it came from. You can construct semicircles like on the slide, and the tangent to the circles will represent their migrated position. Pre-stack migration. It takes into account the location of the source and receiver for each trace when determining the reflector location. Time response could come from any reflection point that has the same total time for the ray path. All possible reflection points lie on an ellipse, with the source and receiver locations being the foci of the ellipse. So pre-stack migration is accomplished by spreading the energy of each time sample along its appropriate ellipse. Time versus depth migration. Both time and depth migration need an estimate of the subsurface velocity field in order for the migration process to proceed. In time migration, the geological environment is approximated by RMS velocity section. The ray bending is disregarded, as you can see on the left picture. For depth migration, a section of interval velocities is used at small intervals commensurate with the wavelength. This automatically takes into account the ray bending. So the main question is what type of migration should we choose? This leads directly to my next point. I'm considering the issue using the example of 3 synthetic models of the Earth with different heterogeneity degree. The first model is quite simple, with almost horizontal boundaries, and velocity is smoothly increasing from layer to layer with depth. The second model is the model of West Siberia, which is known as the permafrost area, and there is a high velocity top layer simulating frozen ground and rocks. And the third model is the model of East Siberia, which is famous for trap magmatism, and you can see traps as high velocity lenses inside the layers. So let's start with the first simple model. On this slide, you can see a stack before time migration, and here is time migrated stack. Pay attention to the selected area. The dip of event has changed after migration. Here you can see a stack after clarifying the velocity function and correcting NMO. The position of the top layer, as you can see, has become even more correct. As shown, the stack is already quite similar to the model. Nevertheless, final result from depth migration with velocity model created with coherency inversion is quite more similar to the model stack. Here you can see the comparison between my final stack and the original stack. They look quite similar. And here is my velocity model and original velocity model. So let's now take a look at East Siberia model. As you can see, due to high velocity top layer, velocity effect takes place. Time migration gives an unsatisfactory result. We still see this velocity effect. Depth migration with velocity section based on Dix formula isn't successful as well. We still see velocity effect. On this slide, you can see depth velocity model created with coherency inversion. And there we have depth migrated stack based on this velocity section. As shown, velocity effect is almost gone, but it's still not like the geological structure. So after several tomography iterations, I finally get the successful result, which is quite similar to the model. Here you can see the comparison between final depth velocity model that I made and the original depth velocity model. Let's move to the last model. Here we have quite similar situation with velocity effects caused by high velocity lenses. Due to this fact, time migration also gives unsatisfactory result. Depth velocity model made by coherency inversion is better, but will still have problems. So after several tomography iterations, I finally got a successful result, which is quite similar to the model stack. And here you can see comparison of the final and original depth velocity models. This brings me to the end of my presentation. On this table, you can see various situations in which it's advised to apply one or another type of migration. Just to summarize the main points of my talk, I consider that without dependence on the degree of environmental heterogeneity, depth migration gives better results because the stack is closer to the observed and all the energy is focused at the real point of reflection. However, don't forget that migration has one problem. Its results are very sensitive to the accuracy of setting the depth velocity model, and time migration is more stability procedure. Also, building a depth velocity model is a very long and complex process. Therefore, using depth migration is not always justified. So, on real data in areas with relatively simple geological conditions, it's advisable to use pre-stack time migration. That's all for today. Thank you for your attention.
Thank you very much, Alexandra. So for everyone, I don't think I mentioned it yet, but for everyone that wants to ask questions, you should at the bottom of your screen have a Q&A box. So feel free to post all your questions there, and then we'll be able to ask them to the presenters themselves. So that's for all of you in the audience. I might have a question for you myself to start off this discussion maybe. So did you already try any of this on real data? So you based your models on Siberia, East and West. Did you also consider already real data to verify that it's also working better there and to see all the effects in the field?
Yes, I had already tried this procedure on the real data, but the stack was quite simple. The geological situation was also quite simple. So I was using only time migration and the result was successful. Okay. But my work, my diploma, I don't know how to name it, it's about migration too, so I will have an opportunity to work with the difficult geological situation with high velocity lenses which are salts. So I will try my best in this.
Yes, of course. Very nice. Are there any questions from either the chairs or the audience?
Yeah, I guess I have a question. So it's actually very interesting results. I'd like to ask you, what do you think about diffraction effect, especially when we talking about third model with such bodies. So don't you think it can change the situation, the diffraction about these objects?
You know, there is no diffractions in my stack, but of course they can be. So the initial stack before migration will have diffractions, but this procedure like migration will so we will see only dots, not diffractions after migration. So it's not a problem. I think so.
Yes, thanks. I guess I understood your point.
All right, thank you very much, Alexandra. If there are no more questions, I propose we move on to the next presenter.
Thank you very much.
Hi, everyone. If there are no further questions, we can move to the next paper. Thank you, by the way, Alexandra. It was a very clear presentation. For the next paper, Yaroslav Brezhnev from Novosibirsk State University will present the structure of the upper crust beneath the Campbellian volcano revealed from ambient noise tomography. Sorry if I pronounced your name wrong. You can start.
You pronounced my name right. Can you see my screen? Can you hear me?
Yeah.
That's great. I will start. Hello everyone, I'm Miroslav Berezhnev, and today I will tell about the structure of the upper crust beneath the Cambernet volcano. In my presentation, I described the object of study. Oh, I can make a point. Then I will briefly discuss the methods and data processing, and finally concentrate on the obtained results and its discussion. About the object of the study. Cambernet volcano is the southernmost volcano in Kamchatka. It is a mafic strata volcano located in the edge of the same-named mountain range. Scientists assumed that the volcano is dormant because there was no data about historical activity, and the most recent pyroclastic material has been dated to 300 years ago. But on the 24th of March 2017, there was a phreatic eruption in which an ash plume spread along thousands of kilometers. Before this eruption, Cambernet had not been studied enough, but there were a lot of studies about geothermal activity surrounding the Cambernet volcano. Area of geothermal activities in this map is marked by green diamonds. In 2018, Institute of Petroleum Geology Geophysics from Novosibirsk deployed a temporal seismic network station to study the structure of the Cambernet volcano and try to find the cause of this eruption. Let's talk about the methods. Noise tomography is based on this fact that for a random wave field with sources distributed homogeneously in the medial, cross-correlation of two continuous seismic records extracts the Green's function between these stations. Cross-correlation, it is a symmetrical related to zero function in the ideal case. And if the station deployed on the surface, in cross correlations, surface waves are predominantly. This cross correlation can be interpreted in the following way. The positive time, it is a signal as if a wave originating in the station A and was recorded at station B. And it's the same situation for a negative time. Before use the cross correlation, we need to preprocessed our real data to converge it to method conditions. Signal processing workflow includes the following steps: filtering, removing instrument response, detrending and demeaning, bandpass filtering, downsampling in order to improve the computational performance. And the most important steps, it is time and frequency domain normalization. As the frequency domain normalization, we use the spectral whitening and spectral widening that transform Fourier spectrum of the signal in the following way. And as time domain normalization, we use the one-bit normalization that saves only the sign of the signal. We need time and frequency domain normalization to suppress the effect of high energy signals, for example, earthquakes, and collides the role of all frequencies and in the bandpass range. Finally, we compute the cross correlation in moving window and stack it in days. We obtain such parallelograms for all pairs of station. For example, in the slide, we can see the parallelograms for this pair of station, and there we can see a stationary signal during the all observation time that indicate high quality data, and this signal corresponds to a surface wave, especially wave waves, and we average all these choreograms among the observation time and derive the mean cross correlation that we used in the next steps of the data processing. And surface waves have a relation between periods of frequencies and velocity that's called dispersion. To use this property in tomography studies, we need to measure dispersion curves of velocity or phase, the group velocity or phase velocity. In this study, we use the group velocity. In the common approach to measure the dispersion for group velocity, it is a frequency time analysis. Frequency time analysis is the filtering of signal envelopes using the narrow Gaussian filters and finding the travel time of maxima on each period, because group velocity, it is velocity of energy transport. This maxima derives the group velocities. In Vietnamese studies, the signal we use negative part of cross correlation or the positive type part of cross correlation or symmetric cross correlation that's computed by averaging negative and positive time. After applied the approximate time analysis, we derive such FTA representations where the black dots indicate the maximus of envelopes on each period. We apply approximate time analysis for all parts of cross correlations to quality control, because all dispersion curves for one cross correlation should be closed. Measure dispersion curves, next step used in surface phase tomography algorithm by Ivan Kulakov to obtain continued distribution of S wave velocity. There we can see that the result obtained from surface wave in this study are closer to results that's revealed from independent body wave tomography studies. To take the resolution of observation system, we apply a checkable test where we made the velocity distribution with high velocity fluctuation and look at how it recovered after inversion. Here we can see that anomalies that we obtain from inversion of real data are closer to anomalies that can be recovered in our observation system. Finally, let's discuss the result. What is interesting in this figure? It is a low velocity in the anomaly in the west flank of Камберный volcano in depression between Камберный volcano and Kashilowski volcano. We suggest that this anomaly corresponds to non-consolidated sedimentary that brought from the slopes of volcano. High velocity anomalies in the east flank of Камберный volcano corresponds to a mafic basement of Камберный edifice, and the low velocity anomalies below 2 kilometers from sea level here and here can be related to water-bearing horizons that feed the geothermal activity surrounding the Камберный volcano. We suggest that this water-bearing horizons, the water from this horizons could be leaked to a magma chamber below the Камберный volcano that have resulted in a rapid boil-off of induced eruption. To summing up, obtained results are consistent with independent results from body wave seismic tomography, current geological information about Камберный volcano, and suggest explanation of this eruption. That's all. Thanks for your attention.
Thank you. Now, if anyone has any question, please feel free to ask.
I do see a question from Anas, but I'm not sure if I understand. So Anas, you say, is it certificate? Please elaborate on your question and then we can answer it live, hopefully. In the meantime, I might have a question myself. I think I missed, Jaroslav, when you did the experiment exactly. Was it for a whole year, or how long did you record the ambient noise?
This record was for a year, but for some station it is less because of some problems with the environmental the Камберный volcano.
So one interesting, I did some seismic interferometry with ambient noise myself some years ago. But one interesting thing I saw is that there sometimes can be a very big seasonal variety. For example, if you look at the winter months or the summer months, you have a completely different signal. Did you observe anything like this yourself?
I know about the season of continuous ambient noise records, but we didn't. I don't know how to say. Second, but if we see in the programs, we don't see any clear seasonable variation in the obtained surface waves from the cross correlation, and we think that these seasonable variations can be neglectable in our studies.
Yeah, I agree. Okay, thank you. It might, I'm not sure if this is true, but if I look at this plot, it might be that in the 2811, 2812, so in the winter months, the signal might be a little bit stronger. So that could indeed be true, I don't know. Anyway, thank you so much. I think we have Anas with us now. So Anas, please go ahead and ask a question.
Thank you very much. First of all, I will thank you for this interesting presentation. My question is for consideration of ambient noise. So what are the steps that you've used to remove the ambient noise from the section? And thank you.
I don't understand the question.
The steps or the filters that you've used to remove the ambient noise. I think about the filters.
Filters and steps about bandpass filtering and filtering. Now in our studies we used Butterworth filters for high pass filter and Chebyshev type 2 filter for low pass filter, because we use Chebyshev filter in order to prevent the aliasing. I can say that the Chebyshev filter such as an anti-aliasing.
I'm sorry, Yaroslav, it seems that you're cutting out. I don't know if you're still with us.
Yeah.
Disconnect.
Maybe I don't. I think I asked the question. No, it is, there was some problem with connection.
Yeah, I think there's a problem with the connection.
Oh, sorry.
Unfortunately, we are running out of time, so I have to cut it off here. Maybe you can still chat with each other via the chat options in the Zoom, so you can answer this question that way.
Okay.
Exchange email or whatever. But I propose we move to the next presenter, which is our very own Tatiana Pertus, who is going to talk about how to image quick relays through seismic methods, and she will present the results from a case study in Sweden. So Tatiana, take it away. Good luck.
Yes, thank you so much, Jono, for the introduction. So here I'm going to share my slides. Can you see them?
Yes, perfect.
Okay. Good afternoon, everybody. My name is Tatiana Pertus. I'm a PhD student from Uppsala University, and I'm going to talk about how to image quick clays through seismic methods. And I'm going to talk about this case in a case study in Sweden. The outline that I will follow is the following. First, I'm going to talk about the context, the motivation of this study. Second, I'm going to talk about what is a quick clay. Then I'm going to describe the methods, and I'm going to tell the results of these methods. And I'm going to talk about the take-home messages from this. First of all, the landslides quick clays usually happens in the northern hemispheres in countries like Sweden, Norway, and Canada. So here I'm going to talk about some examples of the of landslides. This one occurs in occurred in Sweden in Munkedal in 2006. So where all the soil was sliding and produced a crater of 200 meters due to the presence of a quick clay. 26 people were injured and main roads were damaged. So another example is Katmarka in Norway, occurred in 2009 and 2009. So in this case, the whole area of a village is an area of 250 meters was sliding into the ocean. 0 people were injured and main damages in properties were present. So this case is in Canada, the province of Quebec in 2014, in which there was a quick clay slide and a crater of 1.8 kilometers was produced due to this. There were fatal cases and the main roads and properties were damaged. So now what is a quick clay? So here we can see one sample of a quick clay in the normal state. It is usually solid. And then if we look at the particles of the quick clays, those particles are disposed in angular ways in order to get more friction points. And this provides a very stable shape of the sediments. So now what happens if we add we add some load to this quick clay that overpasses the shear strength of the quick clay? So what would happen is that we will get a remote quick clay, which means that the aggregate particles will align and will become parallel to each other, which leads to the liquefaction of the clay, and it will behave as liquid. So one property that is very important to mention is the sensitivity, which is the ratio of undrained, undisturbed to remodeled shear strength. This sensitivity usually is affected by different factors, which are mentioned here, like deletion of salt, ion composition in the pore water, pH level, dispersing agents, and particle shape. This study area is in Sweden, located in southwestern Sweden, very close to the Gothenburg city. It's an area that is close to the Göta River, and it presents smooth changes in the topography. So here we can see in the north side of the area a landslide scar that was occurring some time before. And this area is located about 8 or 7 kilometers north to the historical Göta landslide that occurred in 1957. It was a very big landslide that made all the quick going to the river, and the width of the river decreased. So now talking about the geology, we can see here the geological map. This is characterized by clay sediment that were deposited in the glacial and post-glacial in the Pleistocene. So this is the area that is the study about, and then we can see here the river, the Göta River, which plays a very important role in this case because it goes from the Lake Vänern, which is the biggest lake in Sweden, taking all the sediments along towards Gothenburg. So this is the main transportation way of the river, of the sediments. Additionally, we can see few exposures of the crystalline rock here in red. And as well in the photo area, we can see that we have on both sides of our seismic line, we have outcrops of the bedrock. So the data acquisition, this seismic data was acquired in a 2D profile in which there was used 269 wireless recorders and a land streamer with 120 sensors with a spacing of 1 meter each that were co-located to the wireless geophones and streamer sensors. The seismic source that we used, it was the sledgehammer with a vertical impact over a metallic plate disposed on the road. And the recording parameters were length of 3000 milliseconds and the sampling rate of 1 millisecond. So now here we can see some shot gathers as example. We can see that there is a very low noise in these shot gathers and very high quality in the reflections. Here you can see very clear the first breaks, a refracted P, air wave, and surface waves in this shot gather. These two shot gathers are located in different positions of the survey. This one is more towards the northeast, while this one to the right is going more towards the southwest. So it's possible to identify three main reflections. One of the S1, which is shallower, very close is the S2. Both of them are around 0.4 and 0.45 seconds. And then a deeper one, which is called B1. So now we can see the land streamer data with three component recorders. So it was recorded the vertical, radial, and transverse seismic data. And here we can identify very well different kind of waves. Additionally, we can see all the main reflections, S1, S2, and B1 for each of the components. The seismic processing applied for this data, it was a conventional workflow. First, it was applied a QC as data preparation, then refraction statics, a bandpass filter in order to remove the main noise and enhance sigma, spectral equalization in order to boost the seismic signal, AGC, then residual statics, followed by normal move-out corrections, stacked, balanced to the amplitudes, and a velocity analysis that was looked with the residual statics. And as a post-stack processing affects the convolution and migration in order to obtain the sections. For this case, I obtained the S and P wave sections that is in this data. So here we can see a high quality travel time dispersion for these plots, for this data. So the direct wave is 1,000 meters per second, and the refracted P is 5,750 meters per second. So the reciprocal travel time that I calculate in average is 3.018 meters per second. So now we can see some results about the P wave seismic profiles. So we can identify different interfaces. So one is the one that is called S and the bedrock. But this seismic profile doesn't give that much information about the geological setting. It's a very good marker for identifying at which depth and which interfaces we can obtain. That's why now we have an S seismic section that provides very good detail of the geological setting. Here we can see very, very shallow a reflection S1 and then followed by reflection S2. The reflection B1 is very well delineated and it shows an undulated shape. In order to contrast, we have a borehole in the middle of the section. Some logs were acquired in this section. So here we can see the gamma ray, natural gamma, and the magnetic susceptibility that shows a very high response in the reflections S1 and S2, which indicates that it is a sand layer and a quartz layer. Additional previous geophysical works that was done in the area showed the same, that is a coarse grain layer. So for the P-wave tomography, the method used was a first order finite difference with a total of 9 iterations, and smoothing constraints were applied to prevent large velocity variations. So here we can see one of the reflectors, which is the big one. This is interpreted to be the bedrock because the velocities ranges between 5,000 and 6,000 meters per second. It has a concave and undulated shape and with a low RMS errors, which is between 3 and 4 milliseconds. So now and final conclusions. So here we can see very successful case with the seismic section as image with a tomography that can show us details about the bedrock and the different sand layers interpreted the quick clays. Additionally to this, we can see that this section has a very low shear wave velocity. It's approximately 80 meters per second, which indicates that it's very important to do geophysical studies because it's important to prevent the quick clay landslides. The depth to the bedrock is approximately 50 meters. And this really confirms the interpretation of the later reflections recorded on all different components. Thank you so much.
Thank you very much, Tatiana. I don't see any questions yet. There is time for one question, so I don't know if anyone in the panel have any questions? If not, I do have one myself, so I'll sacrifice my own again. One question, it's related to the fieldwork, specifically to the rolling, how did you call it? The array of geophones, the 3-component one. It's a rolling array, I think you said, right?
Yes, absolutely, it's rolling away.
And how do you make sure that you have a good coupling and you can get good results with such an array? I'm not familiar with it myself, so that's what I was wondering.
Yes, here I can say, first of all, since it is a quick clay, so we have a very good conditions for the soil. Second, those times were not raining, so it was really good weather conditions. Additionally, we planted the geophones, the wireless geophones were planted. So we really dig a hole, put the geophones and put salt on it in order to assure the coupling with the soil. And that's for the wireless. And for the streamer, we deploy them over the road. It's a road that is not a sandy road, is very clean, and yeah, the land streamer is very, very sensitive. So it's very good for recording.
All right, thank you so much.
Yeah, I can see a question in the chat. So
put your questions in the Q&A box down below. And if it's in there, we can quickly answer it still, but we also are running out of time, so we almost have to move to the next session. So Bulek, I think it was, please put the question in the Q&A box and then we can answer it.
Yes.
I do see a comment, awesome, this method will be useful in Iran because quick clays are an important issue in Iran apparently as well. So you have at least inspired someone today. And unfortunately, I don't see any other questions for now. And in the interest of time, I propose we move to our next session. So that will be a session on rock and petrophysics. And that will be chaired by Tatiana, actually. So Tatiana and together with Roberto. So thank you so much for our speakers in the first session. And let's go to the next session.
Thank you, Jono. Yeah, as Jono said, as he introduced us, me and Tatiana are going to present the second session that is on rock and petrophysics. For this session, we have two presenters, and I think that you already know where to post the question in the Q&A section. And now I think I can pass the mic to Tatiana for the presentation of the first presenter, first student. Thank you.
Thank you, Roberto. So then we will give the word to the following presenter. The following presenter is Ali Asghar Shahid from University of Oslo, and the title of it is Rock Physics Analysis and ABO Modeling of HT-HP Reservoir in the Northern North Sea offshore Norway. So Ali, now it's your turn.
All right. Can you hear me all?
Yes, we can hear you.
I'm starting sharing my screen. Yeah. Can you all see this?
Yes.
Yes.
All right. I'll just make it like this. Yeah. So here, just wait. I think I'll just open this. All right. Or maybe like, is it just fine for the cursor?
Yes.
Yes, I think it's fine.
Right.
We can see it.
So, hi, I'm Ali Asghar Shahid from University of Oslo, Norway. And today I'm going to discuss about the rock physics analysis and ABO modeling of HT-HP reservoirs in the Northern North Sea offshore Norway. And I'm sorry, I'm not using the template because it was in a hurry thing. So they exclude that thing. All right. So the authors are myself, Aziz Shahid, and there's another researcher, Munzir Fawad, and our supervisor, Anas Mondo. And so here we go. Just wait. Yep. So the contents we're going to touch, it's first of all the introduction, then the geological setting, and then we'll be discussing the methods and database, and then in the end conclusion and you know, with the results and conclusion. So yeah, the introduction. So basically we're working in the northern North Sea. So there's a graben called Viking Graben, and we have a field there that's called Volumon field. So the purpose of this study is to do the rock physics analysis and Eevee modeling for the specifically high temperature, high pressure, Middle Jurassic reservoir sandstones. And for that, we have used two wells, that is 1023 and 341042S. And the target reservoir for within these two wells is Starbuck Formation, and having depths at 4084 meter in the well at 341023 and 4211 meter in 1042S. So this is the location map for the field. You can see this, and I don't know if you can see it properly. I don't know. All right. So this is the this is the location map we have, the Volumon field, and these are the locations of the two wells. All right. So I'll go really quickly because I have a meeting and I'm getting really short of time because my time was at 1:55 and it's getting up. All right. So I'll just introduce HTHP. What is HTHP reservoirs? They're basically high temperature, high pressure reservoirs. And so far the reservoir characterization for HTHP reservoirs is still limited. So as we know that if it's limited, then there's a possibility, to do something more, to do exciting things for that. And I take that and I try to do it the best I can. So the two distinct features that makes HTHP reservoirs and kind of different from the conventional kind of reservoirs is like they have a high pressure and high temperature, obviously. So the pressure is basically more than 10,000 psi, and the temperature they have is more than 149 degrees Celsius. So this is the figure that you can see that how we basically characterize the reservoir depending on their pressures and temperatures. So we are focusing on this HTHP right now. All right. So now we'll discuss the geological setting. I'll go real quick. During the early Jurassic, we had a really a big global transgression event that resulted in a climate shift from dry to more tropical in the northern North Sea. So moreover, there was a relative sea level rise due to that drifting in the Jurassic period. And in the Jurassic period, our Brand group was deposited. So the Brand group we are basically focusing. So this is the Brand group that deposited in the Jurassic. And the Brand group basically comprises of 5 formations, starting from younger to older. It's Tarbert, Ness, Etif, Rennock, and Broom. And they are more, they're sandstones, but obviously we have some variations in all the members. And this Brand group is basically one of the major hydrocarbon reservoir in the Norwegian oil and gas industry. So this is the Stereographic Map. You can see there with the ages and the curve for the geostatic sea level and the tectonic events that occurred within these ages. Okay, moving forward, we'll discuss the Interfacial Methodology. So far, as we know that in the Volumon field, we are using these two wells, and and we had this data for the well logs we had for both of the wells. So you can see here. I'm not going to discuss that. All right, the softwares we used for the rock physics diagnostic, it's interactive petrophysics, and for the Eevee modeling, we have used Hamsun-Russell. And for the rock physics diagnostic, we are basically using 3 kind of cross plots. That's acoustic impedance versus P-wave and S-wave ratio. That's AI versus VPVS. And then we have used lambda rho versus mu rho. And with that, we've used also the porosity versus VP cross plot. And these cross plots were color coded with clay volume and total porosity and gas saturation parameters. Furthermore, for the Eevee forward modeling, while doing the Eevee forward modeling, we have generated the IG cross plots, and we're going to discuss that later. So the results, the main thing. For the 341023 well, the AI versus VPVS cross plots, We have used a template for shale background, brine sandstone, and gas sandstone trend. So for this particular well, you can see that this is our target, the reservoir we are focusing. It is plotted on gas sandstone trend with lower AI, comparatively lower AI and lower VPVS. Okay, so keeping in this mind, we have color coded the cross plot with gas saturation having 20% to 70% saturation. As you can see that our target is really, exhibiting a really high gas saturation here. Moving forward, considering the same area, you can see here the volume of clay color coding, which we have from 0 to 100%. It shows less percentage of volume of clay. And similarly, in the total porosity color coding, you can see that it is relatively high porous, about 16 to 25%. The well 341042S for AI versus VPVS. Okay, in this we have used the Caprock Heather formation and whole brand group, but we are focusing the target. So I don't know if you can see it properly, but these are the things these points are for the target. So considering this, as you can see that overall the brand group is not plotting on gas and sandstone trend. It's plotting between the brine sandstone trend and shale background trend. So that means the percentage of gas in these in this well in the brand group is not really considerable. It's not really significant. If you can see that here. I don't know if it's here. All right. Now considering this, we have color coded it with the gas saturation. You can see that this is the target that shows that it has a relatively relatively low gas saturation. It's about 31% here. And moving forward to the volume of clay, you can see although it has low volume of clay and high percentage of porosity, but the saturation is quite low. And moving forward to the LMR crosswell, lambda rho versus mu rho, you can see this is for the 341023 well. Okay, the template we are using for LMR is from Goodway 1997 that has a threshold cutoff porous gas sand, at 20 lambda rho value. So the data plotting under this threshold curve is going to be plotting in the gas zone, or we can say that the data plotting here will be considering that as comprising some hydrocarbon or kind of good percentage of hydrocarbon. Okay, so you can see that our target is plotting here in the gas sand region at low lambda rho values and relatively high mu rho values. So considering this, if we move forward to the high gas saturation color coding, you can see that high gas saturation is being displayed in the target formation. Moreover, moving forward to the V clay, you can see similarly low V clay, and with the porosity, it also shows that it comprises relatively high porosity. Okay, moving forward with the same cross plot, but for the 341042S well, you can see that only these two formations, which is active and redness, they are coming with very few points under the threshold cutoff for poor gas sand trend, and our target is here, is not crossing this threshold. So that means we can't consider this as a gas bearing or as a hydrocarbon bearing sandstone. Okay, and moving forward, you can see that although we know that the gas percentage is quite low here, it has a good low V clay and high porosity, but similarly it's low here. Okay, so this is the third cross plot we are going to discuss. This is the cross plot for total porosity and VP, and we are using the cement model here. And you can see that it has a friable clay quartz line and a constant cement model line. There's another line that's called constant cement line, but contact cement line, but it's out of the range of the data, so it's not included here. Okay, so considering this cross plot, you can see that our target is plotting at high VP and high porosity, and it's majorly plotting between friable quartz clay line and contact cement line. So if you color code this target here with gas saturation, you can see that obviously it's showing high gas saturation because this well comprises a gas reservoir. And with the idea to show this cross plot is to just see that if we have cementation, if we have chloride coating or something like that, because we see high porosity here. So that's why we've used this crossword. All right. So the result for the Eevee modeling, I'll really go quick. Now we have two wells, 1034, 1023 and 34, 1042S. So because we have seen that 34, 1042S is not comprising a really good percentage of gas saturation. So for that, because of that reason, we are using in situ condition 80% gas for 34, 1023 well and 100% brine condition for 34, 1042S. And the fluid substitution we have used for both of the wells, for considering for the 34, 1023, the fluid substitution is 10% gas, 50% gas, 100% brine, and 80% oil. Whereas for the 34, 1042S, the fluid substitution are 10% gas, 80% gas, 10% oil, and 80% oil. And you can see this is the Eevee intercept gradient crossplot, in which we can see that we have 4 classes, and both the wells, both the tower in both wells are plotting in the class 4 region. And you can see this is the 34, 1042S tower that's coming in the class 2, and the class 2 basically shows the presence of brine saturation. So you can see that, so the things we are focusing on, the things we are seeing, in the upper slides, it can be confirmed from here. Yeah, it can be confirmed from here. All right. And this is the 34, 1023 points. We have this red is 80% gas, this is 50% gas, and this is our 10% gas. So you can see the trend, it's going in this way. All right. Yeah, moving forward. Yeah, in the end, the conclusion. So the key points we have in the cross plots color-coded with V clay is that the tower formation in both the wells is really low. Like 33%, and but in the 34, 10, 23 well, it's 33%, but relatively high in 34, 10, 42S. Moreover, the porosity we have in 34, 10, 23 well is it's about 25%, and compared to the other well, it's 37%. Talking about the gas saturation, we know that the well 34, 23 exhibit high gas saturation, about 70%, whereas the Tarbert in 34, 10, 42S well as exhibited about 31% of gas saturation. Moving forward, the comparison we had for Tarbert formation, both wells, indicates that the well 34, 10, 42S is considered dry, and because it has a high porosity due to porosity preservation, possibly by chloride coatings. And moreover, the Tarbert formation in the other well, 34, 10, 23, we have considered it as gas bearing, and it shows an AVO class 4 because of several reasons. One of the reasons is like it's really deep. It's like for about 4 kilometers beneath the seabed, and moreover, it has a low thickness, 40 meters, and that might lead to tuning effect while doing the AVO modeling. Moreover, the Tarbert and overlying cap rock, the formation, they become stuffer due to possible quartz cementation, and which resulted in decreasing the fluid sensitivity. That's why we are facing the Tarbert of 34, 10, 23 well in the AVO class 4. So that will be end from my side. Thank you.
Thank you so much. So now we leave the time to attendees to make some questions.
Sure.
Yes. Well, in this moment, we don't have questions, but I have some questions that I would like to ask you, some short questions.
Yeah,
in
sure.
one of the slides, I think that is the slide previous to the conclusions. So you were mentioning 2 oil-water contacts, right?
This one?
Yes, absolutely, that one.
Yeah.
So did you identify that the oil-water contact was in that area, or is like a tendency? So would you like to maybe extend your explanation about the oil-water contact?
These wells basically, comprising gas hydrocarbon. They are known as gas hydrocarbon reservoirs, not as oil reservoirs. But yeah, we have a oil water contact here, and that's really, really little. It's not really significant. Just to, when I included the fluid substitution for oil as well, that showed us this contact. But if you see the petrophysics analysis for this, you will not get oil water contact as a really significant thing. So here you can see, but the petrophysics, it's not really visible.
Okay, it's clear.
Okay. I hope I understand your question correctly.
Yeah, it's quite clear.
Okay.
Thank you so much.
All right.
Yes, is there anyone who has a question? Okay, maybe we can proceed to the next presentations, just to try to be on a schedule. Thank you so much, Ali, for this presentation.
Thank you. Thank you.
So now we will lead the time to our next presentation, which is Joshua Pavodi. So he is from Institut de Sciences de la Terre. So his presentation is hydrogeological properties at the toe of the Nankai accretionary prism using drilling and petrophysical data from hole COO24A IODP NANTRO-SACE project. Thank you so much.
Okay,
so
thank you.
It's your turn.
Okay. Let me know if you can see my screen.
Yes, we can see your screen.
Okay, good afternoon, everyone. My name is Pavodi Joshua from ISTE, a final year PhD student. I'll be speaking about the hydrogeological properties at the top of the Nankai accretionary prism using drilling and petrophysical data from hole C0024A as part of the IODP NANTRO-SACE project. I'll discuss about the location of study, the methodology used, and the results. So the Nankai subduction zone is formed by the subduction of the Philippine Sea Plate under the Eurasian plate, and generally this area has been identified as the locus of slow slip events, low frequency earthquake, and large classical earthquakes. Now, example, we have the Tonankai and we have the Nankai Do 1944, 1946, respectively, all with magnitudes above 8.0. And this location has been the main focus of the NANTRO-SACE project, which is a multi-expedition drilling project that is designed to investigate the fault mechanics and seismogenesis of the Nankai accretionary megatrust. Now, for the sake of this research, we're using data from hole C0024A, which is located at the frontal thrust of the accretionary prism. Now, this well is said to have drilled through the Decolmo at a depth of 830 meters below C4. Now, generally, since we know that tectonic deformation and earthquake cycles are substantially driven by high pressured fluids that are trapped at depth, now it has become very important to understand the contribution of high pore pressure flow generally to fault slip behaviors in subduction zones. Now we're using this well as a form of a boundary to really understand how pressure evolves from higher pressure zone down through zones that have already been identified as low velocity zones to where the location of the well is at the trench. Now, the objective of this study basically is to provide quantitative continuous hydraulic profile along this borehole in order to understand how this property vary across the accretionary prism. Now, to do this, we combine an approach which involves using both drilling and logging data. Now, it is important to use this because it's advantageous. It gives us this ability to be able to relocate hydraulic anomalies to the geological framework, because we're dealing both with time evolution data and depth dependent data. Now, to answer the question around trying to understand continuous hydraulic properties, either pore pressure and flow, is it pervasive in the accretionary prism or just restricted within the Decolmo zone? Now, we use first the downhole annular pressure data, which is basically a data that is being obtained by a pressure that is pressure sensor attached to the BHA component. Now, this tends to provide direct mud pressure data to the operator at the surface real time. So we looked at the data, and it can be observed that the data actually increases with depth with increasing peaks. As a first step of processing, we isolated the first time at which each of these drill depth was reached to know the actual drilling time. So therefore, we're going to employ a systematic workflow which involves modeling of the DHEP data, which in turn will give us information about the fluid fluxes from the formation to the bowl and vice versa. We use drilling data to calculate for the pore pressure profile. Now for self-consistency, we'll combine the results from this and this using the Voslev method to provide quantitative estimation of permeability. So I'm just going to present the results. A lot of mathematical and physics formulas are involved. Now, for the interpretation of DHEP data, we looked at 3 contributions. Now, the first contribution is looking at the hydrostatic clean mud density that is being, the mud density being flowing from by the operators into the well through the drill bit. Now, we look at the contribution of cuttings to the system. Now, it should be noted that this well was drilled with a riserless system, so we don't have direct information about cuttings that are returning to the surface because it's been lost to the seafloor. So we use the mass balance principle to calculate for the weight cuttings, and you can see that we just have little contribution of these cuttings to the original mud. So we've further ahead looked at the hydrodynamic frictional pressure losses when the well is flowing, and we created a model which we compared with the original DHEP data. Now what we did was to take subtract our model from the original DHEP data to have a residual, and you can see that we have this pretty fit from top part of the equationary prison, but right below the decomer we have this increasing pressure data. Now, using a backward model, we estimated for flow, possibility of flow. Now you can see the baseline here, the flow from the borehole into the formation. That's why we have it below the baseline. And but when you start coming down into the decomer, we have this increasing flow from the formation into the borehole. Now, generally, the intensity of flow is being determined by permeability and pressure gradient. Now, so to estimate for the pressure, we use the Eaton's method, 2 independent methods. One, which involves the use of transit time. Now, it is expected for a normal compaction trend that the transit time should decrease with depth, but points where you have the transit time increases, it shows that you have entered into an overpressure zone and an undercompacted zone. Now, with this from our results, now you can see from our results, this follows the normal compaction trend until we get to this point where we had this sudden increase in the sonic travel time method. Now, we estimated our pore pressure using the Eaton's formulas, and then with this we compared our results with the original DHEP data, and we can see that the pore pressure increases even above mud pressure. Now, we also used as a self-consistency the D-exponent method, which tells us more about undrillability during when you're drilling through the well. How easy is it to drill through different formations? Now, it is expected that the D-exponent should increase linearly along the normal compaction trend, but where you have decrease in D-exponent, it is an indication that you have entered into an overpressured zone. So from our results, now what we did was to classify the slope basin facies. We consider that to be hydrostatically pressured. We created a normal compaction trend line going down, and we can see from this point we have this sudden decrease, which is an indication that we have entered into an overpressured zone. Comparing that with the DHEP, you can see this early rise above the DHEP data. So now what we did was we used 2 independent methods to predict for pore pressure, and then we can see right into the decolmo below at the foot wall, there's this increasing pressure downwards. Now, from the DHEP modeling, we were able to estimate for our flow as I showed earlier. Now, we have seen that at this point where the pore pressure is equal to the hydrostatic, the flow we have is from the borehole into the formation, which is consistent for safe drilling. And right below here, we have the flow increasing above 0, which shows flow from the formation into the borehole. Now, we compared the result from the pore pressure and the flow to estimate for the permeability. And it is observed that the permeability generally decays with depth, and where points where we have this sudden bump, it corresponds to around this point where we have sudden increase in pressure, which shows different in compaction within the accretionary prison. Now, looking closely at the Colmo zone, we have noticed this large inflow here. We have increasing pressure here, and we have stepping permeability value. Now we look closely at what is happening at the Colmo, considering the hydraulic structure. Now already it has been identified, we have two strands of the Colmo zone at 813 meters below seafloor and 852 meters below seafloor. Now we identify right below it using the caliper lock data and the VP data and the resistive fracture at this point to look at the footwall damage zone. So we have these two asymmetric damage zone. You can see the shape here and what is happening right below the fault core at this point. We have these two similar, and the resistivity value decreases to a lower value at this point and also lower value at this particular point. So with this, we compared that looking at the pore pressure, we have step in pressure right at the Colmo zone. You can see right into the footwall, you have this, the flow here is consistent at the fault core, while into the damage zone, we have this step in flow, while the permeability here, you can see the step in permeability values. So with this, we have identified the flow intervals here, and then we have identified that right in stepping into the fault, we have the step in pressure value using the two methods. So our inference here is that the fault core is impermeable, and if it is impermeable, that means there's no hydraulic connection between the sediments that are on the trusting and the sediments that are above. So this tends to support more of a lateral flow within the damage zones of the hydraulic structure. Now, looking at the implication to seismotectonics, with what Kitejama did, was looking at how transient pore pressure is as you go from the trench further down to the seismogenic zone. We can see this transient in pressure, and with our results, we can see that we have shown that pore pressure is, we have significant pore pressure, about 38% contribution to the overburden stress, and this is continuous with even higher pore pressure values. So we feel and infer that the possibility that the Colmo zone could be a drainage path for flutes, high flutes, pressurized flutes that are coming in from further depth down to this particular at the toe of the accretionary prison. So in conclusion, we have developed a methodology to characterize the hydraulic states of the accretionary prison using C0024A, using both drilling and geophysical data in spatial time. And then we have shown that the Colmo is an hydroanomalic zone. We have step in pressure to excess of 2.99 MPa. We have the overburden stress about 38%. We have flow to this excess, and the step in permeability value right into the Colmo zone. So we have shown that there's high pressure even at the toe of the accretionary prison, which can favor the occurrence of slow slip events and submergenic earthquakes. And this is just a first step in trying to understand the hydraulic state of the accretionary prison and subduction zone generally. And this method is actually reproducible with other locations to be able to see how pressures and flow evolve with time. Thank you for listening.
Thank you so much, Joshua, for this interesting presentation. So now I want to give the opportunity to the audience to give some questions, thoughts about this presentation.
If no one has a question, I'd like to take the opportunity to clarify just a curiosity. Regarding the possibility of having possible fractures among the Coleman fracturation among the fault. given exactly by these overpressurized fluids in the fault. So I'm going to rephrase that. Do you expect to find, or did you find any form of sort of perpendicular tend to perpendicular fracturation above in the accretionary prism above the Dipole mount because of the fluid that could be addressed to the fluid overpressurization?
Okay, so if I get you, you're asking the possibility of us having fracturation above the Dipole. Now, what I presented here is just staying within the 780 below, right to the Dipole. But if you look at this particular, the structure plane here, we have a lot of structuration right above it, which shows that's why it supports the increase in pressure and flow and down into the Dipole. But then we have this more, you can see the density of fractures even right below within the Dipole zone. It's quite high, which indicates more why we have higher pore pressure right at that. And we expect further down below the Dipole because this well is just drilled to a depth of 871, and further down, the pressure should increase more.
Thank you. Thank you.
Okay.
Thank you.
Yeah.
I have another question. Were you part of the seismic analysis and the drilling part of the project?
No, I was not. Unfortunately, I was not part, but my supervisor happens to be part. So we have this data that is under moratorium, and we're using it for it to be able to make the methodology which we have now, which is a bit different from what has been, which has to do with trying to understand hydraulic anomalies in subduction zone. So I was not part, but I used the data extensively for that.
Yeah, it's okay. It's okay.
All right. I think that now we can already end the session. Thank you to the two presenters. They were very interesting presentations, and we can move on to the third session, that is case studies, hosted by Florencia Balestrini and Ivan Zutenko. Thank you.
Yes, thank you, Roberto. So welcome everyone to the last session of today. As he said, in case of study, I'll be co-chairing this session with Ivan. We will have 4 presentations that will be in the topics of electromagnetic methods and also joint geophysical methods for characterization of different sites. But yeah, I guess we can start with our first presentation. Our first presenter is Monica Sposato from the Università di Napoli Federico II or second. And the title of her presentation is CO2 Detection in Active Fault Zone by Electrical Resistivity Surveys, a case study from Ailano area, southern Italy. So Monica, whenever you want, you can share your screen. The floor is yours.
Thanks. Hi everyone, I'm Monica Sposato and I'm a geophysics student at University of Naples Federico II. I'm also a member of the SEG student chapter, and today I will present you my dissertation work about CO2 detection in active fault zones with electrical resistivity tomography in Ailano area located in the Matese Ridge. The Matese Ridge belongs to the southern Apennines, whose current structural setting derives from an extensional regime that has led to the formation of normal faults that control the formation of the quaternary continental basins, including the Alife basins, in which is situated the study area. Ailano is in a transfer zone between two seismogenic faults, and there is the evidence of minor fault in the hanging wall of the main system fault. This area is characterized by the presence of gas emission, and this can be found at the termination of the primary fault. The isotopic analysis on gaseous samples show a composition dominated by CO2. This confirmed the hypothesis that the CO2 has been generated by thermal metamorphism of the Apulian platform carbonates and subsequent decarbonation. As we can see in the figure, gas vent can be identified in the field thanks to the partial or total absence of vegetation, bubbling phenomena in water springs, and sinkholes associated to the emissions. From previous geomorphological and geochemical analysis, they were built a spatial distribution model for the CO2 concentration in order to make a correlation between the distribution of the gas vent and the orientation of the active faults. Anomalies with east-northeast to west-southwest and west-northwest and east-southeast orientation are compatible with the orientation of the main faults. This suggests that the distribution of the anomalies is controlled by more permeable faults. As I said before, in order to identify possible pathway of CO2 fluid migration, we use the geoelectric method to determine the resistivity parameter, which is sensitive to permeability changes within the damaged zone. The current is inserted into the ground through two current electrodes placed on the ground, and then the different potential is recorded by two electrodes. The four electrodes can be arranged in different ways, obtaining various configurations. We use the pole-dipole configuration as shown in the figure. 2D electrical resistivity tomography survey used aim to evaluate the apparent resistivity both vertically and horizontally. As a matter of fact, the results of a bidimensional electrical survey are represented by pseudo section, and in order to have a real section of the data, the data must be inverted. The survey consisted of 3 bidimensional tomographies. According to the target of the survey, 48 electrode space of 9 meters were used for the first 2 profiles. For the third profile, which was placed orthogonally with respect to the first, 72 electrodes with the same spaces were used. The apparent resistivity data were collected by the IRIS Siscal Pro-Switch multi-channel georesistivimeter, and the 2D inversion of wall apparent resistivity dataset was performed by RES2D ENVE software using the last square deconvolution algorithm. The results of the inversion is a bidimensional model of the subsurface that shows the vertical and horizontal distribution of the real resistivity values. In the ERT1 and the ERT2, we can see anomalies highlighted by black ellipses with resistivity values between 115 and 250 ohm per meters. From the field data, the anomalies can be associated to weathered dolostone, whose resistivity values seems to be influenced by the presence of CO2 in the gaseous state. In ERT2 and ERT3, we see sharp vertical contrast of resistivity indicated by the black dashed lines. Delimited by an anomaly with very low resistivity values between 2 and 10 ohm per meters, relative to an aquifer, and an anomaly with high resistivity values from 100 and 500 ohm per meters, relative to the presence of dolostones. This is a clear evidence of a fault. In fact, by crossing the 3 profiles, it's possible to identify 2 north-south trending as dipping height angle faults, E and B, and the faults B could be confirmed through an elevation profile on Google Earth, which shows the evidence of a slope. Extending this slope, it would coincide with the step placed at the top of Dolostones in Earth 3 and with the one highlighted in the ERT2. 3-4 is it's a buried manifestation of faults. In conclusion, the results of bidimensional tomographies provide a further contribution to the geological structural reconstruction of the investigated area. Based on the results achieved, the electrical geophysical method have proven very effective for mapping the spatial distribution of CO2 in the fault zones. Thanks for your attention.
Yes, thank you very much, Monica, for your very interesting presentation. It was very clear. Okay, we do have a question in the chat for you from Barbara Mandato. It says, hi, I have a question for you. Why did you use the Polo dipole configuration?
So we use the pole dipole configuration because it allows to reach greater depth and to cover more area of the study.
Yeah, and I also have a question. Can I, for answer?
Yeah, for sure. Go ahead.
Yes, about the final cross section or geoelectric section. I have a question. Do you think this? Can you show it, please, one more time?
Yes, sorry. One moment. Sorry.
So I start, as I remember, there was. Do
you see the?
Yes.
Yes, yes. Number 8.
Okay.
Yes. Well, as I understand, CO2 zones have high resistivity. Am I correct? So
yeah.
Does it correlate with gas here or with air here? Or well, what do you think was the reason of this high resistivity?
Sorry, can you repeat the questions?
What's the reason for the high resistivity in CO2 zones?
With Dolostones.
Well, yes, yeah. Yes. Well, now I understand. Thanks.
Great. I have a final question for you, and I think we can then move on to the next presentation if there are no more questions from the audience. I was wondering about the applicability of these results, like what's the next step for this? Like, why are you characterizing this area? Why it's important to characterize and to find these CO2 anomalies?
We can study the area with another geophysical survey, for example, the electromagnetic method or seismic method. Yeah.
But are they gonna take action about it? Like once you characterize these zones where you have these CO2 emissions, like that's what I mean. Like, why is the study made for?
The
once
study
you characterize these, like what actions would people take?
Because we want to study the gas emissions that can be do a problems at the Ailano village.
In the area, yeah, like to have some kind of measurement of it, like yeah, maybe the amount of emissions, or yes, locate them specifically. Okay, great. Yeah, that answers my question. Thank you so much.
Thanks.
Well, and our next presentation is from Orhan Apaydin from Istanbul Technical University. The topic is extracting tomographic images of cavities within cylindrical objects and trees using Georadar method. So good luck, and please start.
Hello, everyone. Can you see my screen?
Yes, we can.
Okay. Yes. Hello, everyone. Today, I would like to present about extraction tomographic images of cavities within cylindrical objects and trees using Georadar method. This project is my actually undergraduate thesis. My partner was Yiğit'tir and my advisor Tugay Seven. Yes, this is my content. Firstly, I will give a brief introduction about the project, and then I will talk about methods. I will talk about method and numerical simulation and laboratory measurements. Finally, I will show the tomographic image, how can obtain the tomographic image. And finally, I will show the results and talking about discussion. Yes, the Georadar is the non-destructive geophysical exploration method, as we know that. So it's suitable for investigate tree, trunk, and another cylindrical objects. The main purpose of this research is to detect cavities and discontinuities within cylindrical objects and trees and produce their tomographic images by using Georadar. Yes. GPR is usually performed along a linear path, but we define a circular measurement geometry in this research. The data to be obtained as a result of the GPR application are the reflection signals originating from the interfaces with electromagnetic impedance difference and their arrival times. That impedance difference is caused by the electrical permittivity. This is the electromagnetic property of the materials. This is the general setup of the models we researched. There are artificial cavity and filling material and a plastic barrel. We did a numerical simulation to see what kind of radar images we would get as a result of a circular measurement setup. For the purpose, the research models are numerically modeled using GPR Max program, which is an open source software to simulate the propagation of the electromagnetic waves through defined media using finite difference time domain. This is my parameters, electromagnetic parameters of the materials. Most critical one, relative permittivity. This is the dimensions of the materials. And this is the measurement parameters, which is the antenna central frequency, antenna type, measurement direction, and measurement interval. This measurement occurs in a circular geometry, so we define the measurement intervals in degree units. It's the 15 degree. Yes, this is the actual models we search, and this is the numerical models. There are receiver and transmitter antenna here, and we rotate these models around its axis step by step with 15 degree, not a continuous skein around this. And synthetic radargrams of the M1 and M2 models. This shown here. This is the reflection from the metallic pipe. If the metallic pipe gets closer to the getting closer to the antennas and the earlier arrival times we get, and if the far away from the antennas, we get late travel times. Yes, we will see this kind of radargram images after the laboratory measurements. We know that. And I will say one more thing. There are 24 radar trace in the one radargram image. This because of the one scale, 360-degree whole scale, and our measurement interval is 15 degrees. So I have a total of 24 radar traces. How can we get one radar traces? I will show a simulation in here, transmitter and receiver antenna. I prepared in a GPR Max program, and the iron pipe, filling material, and one position. I start the scan, and I get the one radar trace. First reflection signals from the outer barrel of the outer surface of the barrel, the second reflection from the iron pipe, and the third reflection caused by the farthest barrel outer surface. And after the numerical simulations, we start the laboratory measurements. This is the laboratory measurement setup. We have VNA device which is produced electromagnetic waves in frequency domain and collect the electromagnetic waves. This is the antenna couple, transmitter and receiver, and a computer to collect, saving the data. This is the actual research material, which are models, M1, M2, M3. M1 contains a metallic pipe, and M2 contains two pipe and metallic and PVC pipe. Why we did it? Because we see if there is a two kind of electromagnetic properties materials, what we'll see this situation. And finally, we researched the 3 trunks sample with artificial cavity within it. I made a simulation showing the laboratory measurements, and we have the rotatable table. We didn't turn the antenna couples around the model. We turned the model around its axis by using this rotatable table. White marks indicate each 15-degree step, and this is the VNA device. We collect the data. After the laboratory measurements, we have these radargram images. It seems to synthetic radargram image results. And yes, we have to ready to obtain the tomographic image by using these radargrams. And we can see the PVC pipes reflection signals in here in slightly, because the electromagnetic impedance difference is less than the metallic pipes. So we can see this reflection slightly. And final model, M3, we can see the inner part of the tree stump, and we can see the artificial cavity reflection signals in here. And finally, by using the radargrams, we obtain the tomographic images. The back projection, we use the back projection method. What is the back projection? This is the method provides reconstruct images using projection of the object from different angles. Tomography is the process of the rendering an object's internal section image by compiling measurements from different angles. This is the equation of the back projection. This is a single radar trace. We have 24 radar trace, and what we did it. I use one trace, radar trace. I placed all radar trace value on the tomographic image, and the second measurement in 15-degree, and I get second radar trace in here, single radar trace, and I placed these radar trace signals in tomographic image by summing up with the previous ones, which rotate 50 degrees. And third step is the same. And finally, use all radar trace. I obtained the tomographic image of the M1. This is the diameter of the barrel is approximately 44 centimeter, and this is the true. This is the range, spatial range, and this is these are the another tomographic image. M1 is clearly we see the metallic pipe in here, and true dimensions. The diameter of the metallic pipe 5 centimeter, and we see the diameter of the pipe 5 centimeters. And the second in the second tomographic image, we see the PVC pipe slightly, because the electromagnetic impedance is the lowest than the metallic pipe. And the last one, we clearly see the cavity in the tree stump, and the shape of the tree stump is clearly seen here. And these are my results. And thank you for interest. Thank you for these professors for supporting of me.
Yeah, thank you, Orhan, for your pretty interesting presentation. We are waiting for your questions, the attenders and organizers. Any questions? So let me start with them. So what possible practical application of obtained GPR results and their interpretation can you offer right now, maybe?
I can't understand exactly.
So, I mean, how we can use it in real life, maybe we can say so.
To detection of the our another main purpose is that to protect the collapsible trees. If the tree has a big cavity in the interior part of it, and we detect these cavities in real life, and we fix the problem by using GPR method. I can answer like
yeah,
this.
I guess I understood your point. And one more question. Tell me more about your signal amplification mechanism. Is this your original design?
Yes, yes, it's our original design, but in the literature there is another application like this. But this geometry is the original.
Yeah, that's significant, I guess. So
yes, we will convert it this research to a paper.
Well, yeah, that's cool.
Yeah,
and we have a question in Q&A section. Hafiz asking what kind of GPR machine did you use?
This is the actual, not a GPR machine. This is the VNA, but it's same as the GPR. VNA produce an electromagnetic wave, and we connect its antennas, two antennas, receiver and transmitter, and we can use as same as the GPR. It's the same process. They propagate the electromagnetic wave and collect the reflections.
Yeah, and one more question. We have at least a lot of questions. David asking, did you see a single velocity value when converting radiograms from the time domain to the spatial domain?
Okay, it's a good question. I will explain in here. I'm not a single velocity volume. I want to use a pen. The radargram, we collect radargram in time domain firstly, but in to convert to spatial domain, I prepare a velocity log. Because this is part of the air. I want to use the pencil, but I can't. Okay, this is the part of the air. So this part of the speed is speed of light, and the interior of the barrel have different dielectric constants. It is 1.1, and the velocity changed. And I used in here velocity of speed, and I used speed to calculate speed of light divided by the squared the electric constant of the material, and not a single velocity value to convert time domain to spatial domain. I prepared a velocity log. Yes.
I see we have a time, so I think we can have one more question. What is the central frequency of the source wavelet?
4 gigahertz. Because the VNA device support us to 10 megahertz to 8 gigahertz range. This is the sweep signal. It's the central frequency is 4 gigahertz. But I think don't use the device antenna support the high frequencies. But for this research, it's the first gigahertz central frequency is useful. Sorry, I answered like
that
this.
was clear.
Yeah.
We have a person, Hafiz Mohammed Nasifi, that asked for your email. So because he thinks it's an interesting topic, so maybe if you want in the chat, you can later arrange that by yourself.
Okay, I can show.
I think you can see. I can see. Yeah, you can see her name in the Q&A, and we have a question in the chat.
This is my email, Mohammed.
Great. I'm sure he can write it down.
I can share
and contact you
in chat. Thank you.
Yes. And Ivan, we have another question in the chat as well. We have a last question in the chat, Oran.
Okay.
From Babulek that says, what about the damping? Did you use the same value on M1, M2, M3? What about the dispersion? How did you mitigate it in each simulation?
I
don't know if you took those things into account. Maybe you didn't for the lab experiments.
No, I didn't use the same values. The question about the numerical simulation, I can understand exactly. 1 and 2, what about calculation? In the numerical simulations, I did different parameters because the M2 have a PVC pipe, and there are one more material in here, and another's is the same, but the PVC pipe is different. I can show the parameters of the materials in here, the left side.
Mm-hmm. Yes. Okay. I guess that probably answers the question. And we can move to the next presentation. Thank you so much, Goran, for your presentation and all your answers. So yes, we move on now to the presentation by Nadezhda Velovesets. I hope I'm pronouncing it correctly, from Novosibirsk State University. This presentation is entitled Study on the Fault Zone Originating from the Altai Earthquake Realized as part of the SEG Field Camp 2021. So Nadezhda, please.
Yes,
yes, we can see your presentation and we can hear you.
Oh, okay, that's great. Good day, everyone. My name is Nadezhda Velovesets. I'm a first-year master student from Novosibirsk, and today I will tell you about study on the fault zone originated from the Altai earthquake as part of the SEG field camp. First, I briefly describe the field camp and the earthquake. Then I will say some words about methods that we have applied. And after that, I will show results and discuss it. And also at the end, I will thank our sponsor and partners. The Altai earthquake occurred with a 7.5 magnitude in Altai Mountains region on September 27, 2003. It was the strongest event in the Altai-Sayan region during the instrumental period of the seismological observations. The village Beltir was ruined. Better understanding of the geological structure in the epicenter area may improve our knowledge about recovering processes and chances of repeating such strong earthquakes in this region. The field camp was called in the heart of the earthquake and was from 17 to 31 of August 2021. The main scientific goal was studying the temporal dynamics of dislocation evolution and refine the structure of the fault zone. All fieldworks and data processing and interpretation were conducted under the supervision of scientists from Trofimov Institute of Petroleum Geology and Geophysics. We made electrical and seismic surveys. As an electrical survey, we made ERT, electrical resistivity tomography. During the field camp, we used Cyber 64K15 for electric resistivity tomography. And in our investigations, we used Schlumberger array and Polo Dipole array with offset of one electrode is about 1 kilometer. Total number of profile lines was 6. They were across the fault. You can see it. The spacing between electrode was 5 meters, and the spacing between lines was 10 meters. Third ERT line overlapped the seismic line. To process the data, we use series and RES3D info. Next, seismic survey. We use the GRM, general reciprocal method, to estimate boundary depth, real-time seismic tomography, and multi-channel analysis of surface waves to estimate velocity distribution. Let's start with GRM. Under the assumption that the medium is layered, refraction boundary and refractor velocity can be determined using calculating plus and minus times based on first break times and applying generalized linear inversion. We used the easy refraction model by Radix Pro to process the data. Next, real-time seismic tomography. Travel time of body waves and positions of sources and receivers are used to estimate velocity distribution on the way waves propagate based on ray theory. During the field camp, we used the active scheme tomographic algorithm Profit by Ivan Kulakov and the ST3D software by IPG-HB RAS. Multi-channel analysis with surface. It is the method analyzes the dispersion of surface waves, usually the Rayleigh waves. And to process the data, we used a software package by IPGG SBRAS. In order to estimate current seismic activity around the epicenter area of the Altai earthquake, we made continuous seismic records to try to identify earthquakes and locate their sources. We used DMAS for seismic data processing. For all these methods, we used a cableless seismic data system Scout. Distance between geophones was 5 meters, and 5 stations for 1 day were deployed. Let's talk about our results. What can be seen on figure is asymmetry, permafrost distribution regarding the fracture. According to results of GRM, MASW, and seismic tomography, permafrost are shallow in the left part of cross-section. There is a clear boundary between permafrost and thawed rocks. Match of boundaries obtained by P waves and S waves indicates to no significant water bearing in the ground. There is an opposite situation on the right side of the cross-section. Firstly, boundaries obtained by P wave and S wave match, but the S wave velocity slightly decreases from first layer to second layer. It indicates high water bearing of the ground. Secondly, according to the seismic tomography results, there is low P velocity for permafrost rocks for the first 30 meters depth, which is less than in the left part. All this evidence can be interpreted as thallic in the right part of the cross-section. Then results of ERT. First of all, there are 2 very high resistivity fields that can be noted on this model. Resistivity value of this matches with typical range of permafrost rocks resistivity. What is interesting there, that there is the area between these fields that lay under the rupture. There is high resistivity, but less than could be expected for solid permafrost rocks and much more for thawed rocks. We suggest that there is evidence of permafrost regeneration during the past 20 years from the Altai earthquake. And also, 4 earthquakes were identified and located. We found that the sources of these earthquakes didn't form a cluster and were located in absolutely different places. To sum up, obtained results are consistent with the main features of the previous research results, but they provide interesting new information about the structure of the fault zone and about recovering the zone. Also, the results obtained by combining several geophysical methods are much more reliable than previous studies. The structure of the permafrost in the fault zone after such a strong earthquake is an important scientific result. We can see that after 18 years, rocks are returning to their original state. It's possible only in very quiet mode of seismic activity, and this is evidenced by the results obtained by seismology. Summing up, we can say that in the area of such a destructive earthquake, there is no serious seismic activity now. We thank SEG, Baker Hughes, and Schlumberger for sponsoring this field camp. Also, we are grateful to the IPGG SBRAS, NSU, and NSTU. Thanks for your attention.
Thank you, Nadezhda. It was a very interesting presentation. Please, to the audience, if you have any questions, you can put them in the Q&A chat box. In the meantime, I have a question for you. I'm impressed for the amount of information and, well, data that you acquire in that field camp. I imagine you were, like, I saw from that picture that you were quite a lot of students. I'm wondering, like, did you process all this data, or was it processed by several students that participated in the field camp?
all this data were processed by scientists from IPGG's bureaus, and also then after that, students who wants can just repeat this data processing and get the same results. Maybe not the same, but the same. And also I have taken part in all data processing, but not really for details, but also I have taken part in result in this scientific results of data processing and to discuss it with scientists from IPGG.
Nice. I can imagine it was a very nice experience. We do have a question in the chat. Please don't use the chat, use the Q&A chat, but we do have one in the chat from Evgenia Terentieva that says, could you please show the dispersion curves used in the MASW processing? I don't know if you have that, like I know you have the velocities profiles that you obtained
yes, I have only these pictures now.
Yeah.
If you want to see the dispersion curves, I can send you, for example, for email, maybe something like that.
Yeah. Yeah, but I guess those profiles are the ones that you obtain after inverting those dispersion curves.
Yeah,
right?
yeah. Okay, of course, yes.
Yeah, great. Yeah, I don't know if some of the panelists have any other questions. We have some more minutes. Otherwise, I do have another question. Can you show the last results of the, I think it was the EM or the resistivity tomography that you have after this?
Okay, this?
Yes, you had these two like big anomalies from the permafrost, right? As I understand correctly.
Yes, it's
and
permafrost
you have
rock. Yeah.
exactly, and you have in the middle this. You mentioned this that it's not visible exactly in the middle. I don't know if I didn't catch it or so. If that's the case, can you repeat it? Why do you know why that can be?
What can be like this zone with low resistivity? Because of fault zone.
Oh, that's the yes. Great. No, yeah.
It's a deep fault that's recovering for now since Altai Earthquake.
Yeah, that's very clear. Thank you. Yeah, I guess then if there are no any more questions, we can continue to the next presentation.
Yeah, and last but not the least, today is Sofia Davydenko from Russian State Geological Prospecting University with application of UAVs and ground geophysical methods in the study of the ancient metallurgical complex in the Barukhal 2 Western Baikal region. Sofia, if you're ready, please start.
Hello. Hello, my name is Sonia Davydenko and I'm a fifth year MBA student, and I would like to present you my report of the topic, the use of UAVs and ground-based geophysical methods in the exploration of the Asian metallurgical complex at the Barukhal 2 area. The content of my report is present on the slide. In 1997, on the western coast of Lake Baikal, near the village of Sharatagod, there was unveiled a monument to the Asian metallurgical Barukhal 2. According to the radiocarbon methods, the age of the monument is more than 1,500 years old. One of the problems of study Asian geological complex is bigger area of location. The possible solution of these problems is the use of geophysical methods to study archaeological sites. During the period, two types of pit furnaces were used: funnel shape and double pit furnaces. For the first type, we built in the ground of the edge of an artificial subhill pit. These furnaces chambers funnel shaped. The archaeological value of the object line is fast that was used the Han technology during the construction. The archaeological complex has a complex shape, and we used this model for taking next. Okay. Some of filed program was compiled. The host rocks have a low magnetic susceptibility and resistance. The board walls of the hairs clear and having very high values. The complex is consisted of electrotomography, electromagnetic scanner in the frequent domain, and continuous magnetic service and magnetic exploration of the Eevee, but NAMPs don't not give clear result. At the Brunhall 2 facility, the goal was to select the optimal service technology for which various methods of electrical prospecting and magnetic prospecting were performed. We calculate the direct problem for a cube maturity 2 by 2 by 2 meters and a depth of 15 centimeters. The center of the anomaly is offset from the object due to magnetization. The anomaly at the distance of 1.5 equals 300 nanotesla anomaly at an amplitude of 7.5 meters, 5 nanotesla. The anomaly stands out well, which makes it possible to use the UAV series for the archaeological era. We use consider the direct problem for electrotomography. The Dipole setup, the Schlumberger and Finner setup we use it. We settled on Dipole. Then the problem of choosing the optimal network of profile was solved for placing a Dipole. We made an estimate of the sensitivity to the object dependent on the distance from the profile. The maximum distance between profiles not exceed 5 meters. Electrotomography was performed on 9 profiles with a step for 2 meters. There is not a great anomaly since the forge was opened and the electrotomography, electromagnetic prospecting were violent, but there is a good anomaly from the log forge. Then ground series and UAV series. We can see the regional background of the UAV, and on the map of magnetic pellets is obtained from the ground series. The regional background is not observed because the construct of the anomalies is higher the objects are clearly visible. Moving on the 3D interviews results, electrotomography was asked to make two inversion in the zone 3D and Airtel Lab software. The thought is stable. The best result of inversion of electrotomography is observed at a depth of 2.5 meters as at depth of 0.5 meters. In addition to anthropogenic traces, seasonal and permafrost is also visible. At a depth of 10 meters, permafrost is visible. Let's go back to magnetic perspective. In the process of inverting the UAV data, the background of the formation was removed and the location filed of the first meters was highlighted. Based on the result of the inversion of the ground-based magnetic prospecting, the anomaly from archaeological objects were identified. Then the inversion was carried out in the QGI Kappa program, then by my grandfather. We see that ground-based and element magnetic surveys coincide. It confirms that it's possible to use UAV surveys to search for metallurgical forge. On the AA project line, all objects from anomalous are depicted where the vector parallel the geological object. When the have different angles, it's archaeological objects. And on the slide, we see that result of magnetic surveys, inversion, and electrotomography, the objects are clear, visible by the both of these methods. And conclusion. A simple 5-figure model has been completed. The calculation of the DX problem from magnetic surveys and electrotomography from a simple filed model for the data as we dimension data inversion was performed as a result of which the remained magnetism vector was determined, and according to the result of electrotomography at the depth of 2.5 meters, as a result of the diminution inversion of the magnetic field with the determination of Riemann magnetization, it is possible to celebrate archaeological and geological objects. And surveying the magnetic field used UAVC and ground-based magnetic surveys and applied effective for localization anomaly object and determining the magnetic prospecting. And that's all. Thank you for attention.
Yeah, thank you, Sophia. We're ready to read any question in Q&A section. So, anybody? So, well, let me ask, what rocks are represented in the background of the electromagnetic anomaly itself.
Mm,
So, what?
okay, I understand. The walls of the porch are representing by fire, clay, and lime. Clay, lime, you know, and when fire, they, I don't know English word. This, but it's baked there.
Okay. I'll ask Sophie in Russian and then translate your to you. So, Сонь, какие породы, ну, то есть это уникальный случай того, что вот так хорошо выделяются эти печи на фоне пород, или это не уникальный случай?
Нет, такая ситуация, ну, здесь рассматривается ситуация того, что горно хорошо выделяется за счет того, что у него обожженные суглинки и глины на стенках горнов. Из-за этого мы можем их определить при помощи геофизических методов. И именно вот такой вот комплекс геофизический Бурнхау-2, ну, который мы изучали в данной работе, он является уникальным, потому что ранее не было обнаружено в регионе, в данном регионе, при Альхоне, подобных горнов, ну, в изучении их.
А вмещающие породы какие?
Вмещающие породы, они, ну, вмещающие вокруг это, господи, известняк, песчаник, вот. Но глубже уже метаморфические породы идут.
So background rocks are limestones, and that's why we can see such a good contrast between furnace with iron and non-magnetic limestones.
Thank you, everyone.
Yeah, so that was our, as I didn't see, don't see any other questions, we can let Sofia go and say that our conference are coming to the end. Now it's wrap up and closing remarks time and discussion in the chat maybe. Yeah, and about results, our judges now rating and evaluating your works. I think we must give them some time to vote. So please don't leave and wait some time for the results. Thank you. I see we have results, so let me proclaim them. The first place with the score 36.57 points have Orphan from Istanbul Technical University. The second place have Joshua from Instituts de Sciences de la Terre with the result of 38.189 points, and the first prize have Monica from University di Napoli, Federico the second, with the higher score of 38.93 points. So my congratulations to Monica and I guess if you hear us,
yes, I hear you. Thank you.
So yeah, it was a really interesting presentation, but everyone who didn't get their prize place, don't be moody. It's not the last your presentation. So thanks for everyone who attends and who presents today. So
thank you for all.
Thank you.
It's a nice experience for us. Thank you.
So yeah, I guess for today it is all. The reward will find the winners soon, I guess. One more time, thanks everyone, and I guess goodbye. Maybe see you next time. Yeah, and the recording will be on YouTube channel.
Bye-bye.